In this lesson, we're going to talk about optimizing our SOPDT fit to data. If you remember our first order plus dead time equation, we had three constants. Here we have four. Kp, tau p, or actually tau s if we're being honest, zeta, and our dead time. All these combine in this equation right here. Similar to what we've done before, all we're going to do is have a function that calculates our derivatives, mainly our derivative and then the derivative of our derivative at any point. We'll have another function which simulates our system using ODE 45, and then finally an objective function that takes as an argument one array of our guesses, and then with that function it simulates what the function will be like and minimizes the sum squared error between what we think our system is and what it actually is. So we'll go ahead and we'll just work through an example of that together. So we have clear all, close all, CLC. We'll go ahead and we'll create a system with actually just we're doing the same thing. We're going to use our sim process data function. In fact, let's go ahead and look at our functions first. So we have our process here, which takes t, even though it's not used, so we can go ahead and change that to a tilde. We have m, which is going to be the magnitude of our change, n, which is the number of time points that we have within our system, u is going to be the input value, kp is the process gain, and tau p is the process time constant. So that's our process. If we sim process data, we're going to assume it's a 10th order system. We've got kp is equal to 3, a tau p equal to 5, and we're going to store our predictions in this yp. We'll go ahead and change this t to a tilde as well. And then our SOPDT system here takes t as an argument, x as all our integrated variables, so that's going to be the derivative and the second derivative, or so I should say, because our second order is integrated derivative is integrated to make our first order derivative, it's going to be our output y and the first order derivative. Then we have u, which is the input, kp, tau s, zeta, theta p, the t values, as well as xp naught, the initial point. So we go ahead first and we account for the dead time here using interpolation or 0 otherwise. We go ahead and then we say y is equal to x1 minus xp naught. dy dt is equal to x2. So we unpack x into first the actual value and then the derivative. The first derivative right here is dy dx. dy dt, our second derivative, we calculate as this system right here, and that should look familiar. That's really what our system is it's this second order system. And then we put it into this dy is equal to this column vector. The whole concept here is integrating the second derivative gives us the first derivative, and this first derivative integrated gives us our y at the next time point. With sim model, we go ahead and we plug in these values as arguments, and we go ahead and we loop through the series with ODE 45. Finally, our objective function, we have sim model and our objective, where our objective is the sum squared error at each index between sim model and this yp, which is our process variables as we have the data. So we go ahead, we simulate this 10th order system with inputs u equal to 0 and then equal to 1, 0.1, and 0.5. So we see that on the right here, our output and our input. We go ahead and we have data saved as a matrix and we plot it. Then we take that data and we read it. We'll specify the number of steps and the delta t within that system. Our p naught is going to take guesses for 3, 5, 0, and 1. And it's important to be at least reasonable. So we go up to 3, and it looks like our steady state value is going to approach 3. So a gain of 3 is a great guess. As far as tau p, zeta, and theta p, well, theta p is coming from our dead time. And at dead time, it looks like it reaches the inflection point about here. So a guess of 2, I'd say, is reasonable as well. The tau p and zeta are the two that we need to use some correlations as we've done. And really it's just about getting a close enough measure so that we're able to guess. Because we approach so fast to our point, I'd say that we're either overdamped or we're right on damping, and so I think a zeta guess of 1 is perfect. And then to get from zeta to tau p, we'll go ahead and just look at kind of how things progress as far as progressing to that point. It's not a great, it's not the best way, how can I say? It's not fully accurate, but if we look at the process time here, it's going to be about, if we start here, it's going to be about, or if we start here because of the dead time. So if we start at about 6 or 7 and we go to about 63% of the way there, it's going to be about 3. But it's 1/3. And so I think just guessing with 5 is good. That's what we do here. The whole point, though, is that we could take our correlations, which we mentioned earlier, and do it. We'll do that in the next exercise, though. So the whole point is we take some guesses for what our 4 values are. We plug them into our objective function. We use fmin search, and then we're going to graph the two and look at the results. So we'll go ahead, we'll run this section. We'll go ahead and look at our results once fmin search finishes. So there you have it. In red, and I'll make it even bigger. In red is our final solution. These dots are our process data, the black dots I should say, and the blue line is our initial guess. So you'll see our interpolation matches up very well. And in addition, our fit is remarkably well. So we can approximate a 10th order system with a second order system very well. If we were to do a first order system, I doubt we'd get quite as close. We'd have a little bit more of a flattening going on. So the second order system helps us approximate processes fairly well. And we can do it using fitting to data using solvers as long as we create an objective function that's a function of those parameters that we want to fit to. Hopefully this has been helpful. Let me know if you have any questions.